And some people only go as far as confidence intervals. They actually don't like the idea of rejecting or not rejecting the null hypothesis. They don't actually like that approach. Also, you'll find confidence intervals are used in the evidence-based approach. Have you all heard that sort of term? You often hear it on TV when they're reporting results of studies in the medical field and so forth, policy making as well. They talk about the evidence-based approach, where rather than just have one single study where you reject the null hypothesis, there's a sort of move in certain fields to actually look at many different studies and look at, do meta-analyses, for example. So, have you heard of meta-analyses? Yeah. No? Where you actually put together many, many different studies across the literature, and you do some sort of computations there across many different studies to try and see if there's a pattern going on. So there's particular analyses sort of associated with that. We're not going to cover that, but it's quite good to be aware of that. A rather different approach, rather than a single sort of study with a null hypothesis rejected or not. You look at the sort of pattern over several studies. And confidence intervals are usually presented in that approach. Okay. So when we're doing the ANAVAs that we did in the first few weeks, and indeed you've just seen the ANAVA table on the multiple regression, we're testing, with the ANAVAs, we're testing whether the population means are equal or not. So for each condition of our ANAVA, what the underlying sort of theory is, are the populations from which we've sampled them, are those population means the same? That's the null hypothesis. And we look to see whether we can reject that or not. But with the confidence intervals, what we'll get is a slightly different approach. So instead of a sort of single estimate of the population mean, which is what you get from your sample mean in ANAVA, yeah? Remember, we look at the mean and we say, are there any differences across conditions? You're looking really at a single point estimate. But with confidence intervals, do you remember that you kind of get an interval estimation? Remember that from last year? So some people would argue that it's a lot more balanced, but it's worth remembering that it's still a probability. Okay, so it's still an estimate. So you could say something like, if you did a confidence interval, you could say something like the interval 20 to 24, say, if you had some sort of measure. If you assume you've done a confidence interval, you could say the interval 20 to 24 estimates the population mean with 95% confidence. Does that ring some bells from last year? Yeah. Okay, so that's the kind of thing you might be saying if you're calculating a confidence interval. You don't say I'm 95% confident. Strictly speaking, you should be saying it's sort of more worded in this way. Usually we have the 95% confidence intervals, but you can make the interval larger, in which case you'd be more confident that you've got the population mean, that you've estimated the population mean. So has anybody ever come across a journal article where they say the 99% confidence intervals? No, most usually it's 95, but you could use the 99% confidence intervals, but in this case your interval would actually get larger, say from 18 to 26. So it's a bit less precise, but you were estimating the population mean with 99% confidence.
You can never use 100%.
No, because that's why I say it's still probabilistic. There's still a possibility that you've made an error and that your population mean is not in that confidence interval you got. Okay? So there's still always that possibility. Now we can get SPSS to give confidence intervals. I think we use descriptives. It'll give you the lower and upper cutoffs. I think you might have already seen those on the printout. And it's nice when it's plotted visually because you get a better idea. You probably did it for a t-test last year. Did you do it for t-tests? Maybe remember that you've got confidence intervals there, the upper and the lower boundaries. It's calculated, obviously, we don't have to calculate it by hand. So did you do one by hand at all? I think Dancing really might do one by hand. It is calculated a little bit like the stats test. I mean, you can have a look in Dancing really, but we're not going to learn how to do it. we will just click buttons in SPSS. I think what I've got on my handout is some confidence intervals for the naming experiment I've been using. So actor, actor plus character, and actor plus series. So what design is that? Is it within or between? Between, yeah. So people were randomly allocated to conditions. And it is the case that SPSS is better at providing with more information for between designs. So you can get the confidence intervals quite easily for between participants' designs. So I'm going to stick to between participant designs confidence intervals for you to actually illustrate them. You can do them for within subjects' designs, but actually it involves an extra calculation that SPSS doesn't easily do. But I'm not suggesting, I could give people, if anybody was going on to do that, say next year, I could give people a reference to how to do it by hand for within subjects' design. But don't worry for PY211. Okay, so assume that I put the data in from that analysis in and click the button in descriptives in SPSS, and I got some confidence intervals coming out. So I went into descriptives in SPSS and said, yes, I want some confidence intervals. And you probably, if you've got your printout with you, those of you at the back, you can see here it's given us an upper and a lower boundary for each of those conditions. Okay? So that is the confidence interval. So we're saying that this interval from 809 milliseconds, remember it was a dependent variable was milliseconds, to 915 estimates the population mean from where we sampled, don't forget, estimates the population mean with 95% confidence. And here's another one there. So you can see there's the lower and the upper boundaries, okay, for the confidence intervals. But nicer to see it visually. There they are. Okay, so I did ask SPSS to draw a graph. So then we've got the confidence interval for this between participants design one factor. But of course we've now got 3 levels. You can see that these two overlap quite a bit. But little overlap there. These are the confidence intervals around the mean. So strictly speaking, you shouldn't really use them for significance testing. Okay, you shouldn't really. But when there's very little, when there's no overlap at all, actually you can say those two population means must differ. They're different populations. So if those two didn't overlap at all, then you could actually say those population means for those two conditions are different if they didn't overlap at all. But strictly speaking, with these confidence intervals around the mean that we got from SPSS, you shouldn't really make decisions about significance testing. But you could in the case where they didn't overlap at all. This one's a lot wider than that one, isn't it? Did you comment on that sort of, if your confidence interval is quite wide, and in a way it's experience that gets you used to that, it actually suggests that one condition was a bit more variable, a bit noisier. You've heard me use the word noisier, haven't you, when the data is a bit more variable and messy. We've got quite a slightly tighter confidence interval there than there. So you could infer that there's quite a bit of sort of noise going on in that condition. And you might want, it's quite a large confidence interval, you might want to replicate the experiment and sort of bring that sort of noise down a little bit, control, maybe introduce a little bit more control, or maybe a bit more practice. Do you remember they had the learning block? Maybe they need more practice at learning the names. And that would have reduced the variability a little bit in the naming block. Anyway, hopefully that's refreshed you back. Just looking at the confidence interval around the means. So within that interval there estimates the population mean for condition 1 with 95% confidence. You could say something like that. Okay. So avoid using these confidence intervals around the mean to talk about significant differences unless they completely overlap or don't overlap at all. So otherwise you shouldn't really use them. What you could do instead is use confidence intervals of the difference between means. So when you do your t-test, for example, between two means, you can get SPSS to print out the confidence interval of the differences between the two means. So can you hear the difference? Rather than a confidence interval around each mean, you can then get a confidence interval of the differences between the two means. And that would be a different confidence interval. Can you see here, supposing I've done it for actor versus actor and character, can you see that this confidence interval does not contain 0? So that interval, minus 247 to 28 milliseconds difference, to minus 28. Do you see that? That's, assume that I press the right button on a t-test, ask for confidence intervals for the differences between two means. You can see that the differences range from minus 28 milliseconds to minus 247. And so that interval does not contain 0, so there are no 0 differences between the two means in that interval. So therefore, you could conclude there's a significant difference, because that confidence bound interval does not contain 0 differences between the two population means. So that's slightly different. That's confidence intervals for a rather different statistic, the difference between means. Did you do that last year? I'm sure you did. Did you talk about whether a confidence interval went through 0 or not? Yeah. So, coming back to that evidence-based approach again, that I mentioned, sometimes it's really quite important to get an idea of the actual value of the population mean. So remember, when we just do ANOVA, we get a single point estimate. Our sample mean is a single point estimate of what the population mean. But when you do the confidence intervals, you get a lower and upper boundary. So it's giving you a bit more information. And, you know, in certain pieces of research, it might be very useful to get a much better idea of the possible values of the population mean. So let's say you were doing some sort of reading intervention. You were looking to see whether phonics or some other new reading intervention with young children improved their reading, say. And you did your experiment, you got some data in for a control group of children and the children who had the new intervention, and you did your t-test, for example, and you found that your confidence intervals for differences range from 2 to 4. So yes, it doesn't pass through 0. So it doesn't go through 0, so it does look like there's an effect. But if you were knowledgeable in that area, you might say, look, okay, so the population mean could be 2 points difference between the experimental group and the control group, or it could range up to 4. But 4 really isn't much of an improvement in reading, and therefore it's such a small sort of value that I'm not actually going to, it's too expensive to introduce this reading intervention across the nation if it's only going to lead to between 2 and 4 points improvement. So it might be, in some instances, having that range could be quite useful for making that kind of decision, rather than an exact sample estimate. Okay, I've already said confidence intervals in more complex designs. I've already said something about within participants' designs. But we should be able to get the confidence intervals around each mean for a 2-factor between subjects design. So, just moving on a little bit, we should be able to click on some buttons, which I probably don't even dare go into actually just at the moment. Who's got their additional notes with them? So I didn't bring mine down. I think I've put some instructions there. Yeah, page 8 of the confidence intervals additional notes. I might in a minute try going into it, but I don't want to get stuck in a loop. So can you see on page 8, you've got some instructions there as to how you could get some confidence intervals for your between participants 2-factor design if you were doing eyewitness. page 8. Can everybody see that there are some instructions there? You just go to graphs. The disadvantage is that you actually have to, I couldn't really seem to get it to do it with a line graph. So those of you who felt you wanted to have a go at confidence intervals, and it is optional, it might, you know, if you don't do it properly and you demonstrate a little bit of understanding, you have to redo your graph as a bar chart, because I can't seem to get confidence intervals in SPSS 20 using a line chart. But it's very simple to do a bar chart, and I've given you the instructions there. Mike did give you an example of a bar chart, didn't you? And in one of my SPSS printouts, I also did a bar chart. So, and we did it in class. We did do it, didn't we? And some of you said, "Oh, I prefer that." Yeah. But so if you wanted to do the confidence intervals, I've got the instructions there in SPSS 20. I think I had a go in 18 at home quickly, and I think if you use a chart builder under graphs, it seems to work. It's pretty similar. Okay, so you might be able to do it at home on 18. And then you could have a look to see if any of them were non-overlapping, for example. I don't know, it might be for the Lebanese accent versus no accent. You might well find that the confidence intervals don't overlap. Have you done them? Excellent. Have you put a picture there? No, but you've done them. Excellent. So you read it in advance and you had a go. And did it work in 20? Or did you do it at home in 18? You did it in 20. So someone's already worked through the instructions for the eyewitness data, done a bar chart, and got the confidence intervals and had a look at Lebanese in particular, and they don't overlap. Okay, so if you, that's good, hold on. So if you were doing them, fine, most people can click buttons and get them out, but try and make just one meaningful comment to demonstrate to your marker that you understand a little bit about confidence intervals. And as I say, you know, if you've looked at the criteria for how we were going to mark the labs, you'll see in the results criteria, you know, it'd be showing depth of understanding. You know, if somebody's got everything correct and they're showing some advanced understanding or depth of understanding, that's the sort of thing where you might push up into a third for that section. The marker might be thinking, oh, that's impressive. But if you did them incorrectly or demonstrated a lack of understanding, okay, we say we're not going to take marks off if you don't do them. No, we wouldn't. But you wouldn't push up if you wouldn't have marks taken off. But if it's clear that you don't actually understand them, then having partially done them won't get you anywhere. So both those are optional: simple effects and confidence intervals. Any questions on the confidence intervals? We're just going to, you can of course do them for correlation as well. I think that's my next slide. But are you just thinking about your eyewitness? How many people think they might have a go?
Can you use this in the mindfulness?
Can I
use this in the mindfulness?
In the mindfulness?
The mindfulness.
Yes, good, yeah. I did say to James, you know, I'm just going to show them quickly the regression as well. Yeah, so of course, you know, confidence intervals aren't restricted to when you're looking for differences across conditions. You can get them for more or less any statistic, and you can certainly get them for regression coefficients. So, I think I'll put it in my additional notes, but you can ask SPSS for confidence intervals in the regression house. In fact, when I had it up on the screen, do you remember I mentioned, can you see on the descriptives, I think it was, when I did the regression on the screen earlier on, there was a little box to tick for confidence intervals. Did you see that? Anyway, there is. So it's very simple. And what it will do is it will give you the confidence intervals for the B coefficients. Remember the last bit in the analysis before James came in, we had a table of coefficients, didn't we, for the regression. And I talked about the standardized betas. And then I pointed you over to the left-hand side of the table and said there are also the B values that we were looking at last week, the unstandardized B values. Okay, so you'll see those on your table of coefficients. If you click the button for I want some confidence intervals, please, then you will get confidence intervals around those B coefficients for each predictor. So, what are your predictors for James? I know he usually alters the lab slightly each year. Just out of interest, what are your predictors?
Attention control.
Attention control. And sorry, attention control.
Anxiety trait.
Trade anxiety. And the third one? So you've got those three predictors. I don't know whether you're going to use all of them in multi-regression. That depends on any collinearity. But hopefully, that's probably what James is hoping to talk to you about today, how to do the analysis. Anyway, if you and what's your criterion for James's lab? Mindfulness. Okay, so you're looking at which of those three, whether those three predictors jointly predict mindfulness, and if so, which of those predictors is the most important? That's probably what we'll be doing next week. But yes, you can ask for confidence intervals for the B coefficients. And so, for example, in my reading data, my reading example I've done with you, I went back in and I asked for some confidence intervals for the rhyme predictor. And I got, here they were. I mean, again, I'm not going to do it on the screen for you, but the lower boundary was a correlation of a B value of minus 0.2.271 to plus 1.22 fold. So that B value for rhyming is correlation with prose reading passes through zero, doesn't it? So there are some negative correlations. Within that boundary, some of the means could come out negative or positive within that boundary. So because it passes through zero and you're getting some negative and positive, then that's indicating to you that no real sort of predictor there, because it includes zero prediction. Can you see that? Yeah. So what we're talking about when we talk about the confidence intervals, you could think of it. Let's say you did when we talk about the 95%. We talk about 95% confidence. Imagine that you've done 100 sort of replications and worked out 100 B values. So let's say you kept on going into a huge chunk of data and working out a B value for each one. You did 100 separate analyses. What you're really saying is that in 95 of those, 95% confidence interval, 95 times that interval will contain the population B value. In 5% of them, it won't. That's kind of what we're saying. Same with ANIMA or t-test. Let's say that you've done 100 sort of samples and calculated the sort of estimated population mean from your sample. You've done that 100 times. What you're saying by the confidence interval is in 95 of those separate replications, 95 of those, the interval that you've been given by SPSS contains the population being, you're estimating at 95% confidence, but 5% of the time, that boundary it's given you won't contain. It's wrong, it won't, it's in error. But here, so here you have got some confidence intervals for your B coefficients, and hopefully James will be able to, we'll have a look at those next week because you'll be doing the success. And here you can see it passes through zero. So you could, obviously, if you came across that, you could say, so clearly, there was some positive and negative correlations in that boundary. It's not useful as a predictor at all, is it? So you could do them for the regression lab, and again, those of you doing that would be just that little bit of extra. It would be optional. But if you could do that and make a meaningful comment to demonstrate to your marker that you understand confidence intervals, then that will be, just show a little bit more of advanced understanding. I think James is going to go through something else with you, as well as another option for some of you doing that lab. Did you mention partial correlations? No, I think that's probably what he was going to do. So, confidence intervals useful because it gives a range of values for a population mean or for a B value in regression, not just a point estimate like ANIMA. Gives you the sample mean is a single estimate of the population. It can give you information on the pattern of the means or on the value of B. For example, completely overlapping confidence intervals suggests any ordering of means in an experiment. If they completely overlap, you could have any order between the two conditions. No significant difference. If they don't overlap at all, then yes, you can infer there's a difference in the population mean. And if you're looking at the confidence interval of the difference between two means, or of a correlation coefficient, then it's useful to see if it's going through zero. That will tell you something too. Also, if the confidence interval is rather large, then it could indicate a noisy experiment. You might want to repeat the experiment, cutting down on extraneous noise, perhaps giving people more practice, making sure that the conditions are sort of much quieter, etc. And experience, I mean really only experience will help you to say, well, how large is large? But that will come with experience. So, there we are, and that was the point I was just making. So I've extended your knowledge on a little bit to, for example, how you might get confidence intervals for two-factor designs, and also talked about correlation a little bit and the b-values that you're going to be recognizing. So you should be able to do it for the lab if you wish to. Okay, I'm going to talk about another sort of related topic, effect size. Did you do a little bit on that last year again? Because the point is, you can get a significant result, but it may not have any real, it may be a very, very weak effect, and it may not have any practical significance, particularly if you're in applied research, like I was just talking about with the reading example. So it's another thing that over the last 20 years or so is being pushed, by some psychologists, and it's particularly the American Psychological Association, the APA, are very keen now to see a measure of effect size when people publish their. And presumably you were taught last year to try and give a measure of effect size. Did you do a little bit on effect size? There was a t-test. Yeah. So do you remember D? The D? If you look at the difference between two means and you divide it by a standard deviation. Is that Cohen? Did you hear about Cohen? He was one of the main people pushing for you really must report effect size because something can be significant and have no practical or theoretical, there's such a weak effect that, there's very little sort of theory that could be affected or applied, might not have any value. So it's quite easy for correlation. Did you know that R is actually the effect size? Did you do that last year? That the value of R, Pearson's R, is actually it's a descriptive statistic, and it actually is the effect size. So that's simple for R. 0.2 plus 0.2 is that a large effect size, weak effect size, moderate effect size. Plus 0.2. Let's assume it's significant. R equals plus 0.2. What kind of effect size is that? Moderate, strong, weak? Weak, yeah. So I'm sure you touched on that last year, and again, you can keep that in mind for this year as well. Because if you've got a very large sample size, it will easily come out significant. And the same if you were doing ANOVA or t-test. If you have a very, very large sample size, any tiny little difference could come out as significant if you increase the sample size. You're going to get a significant difference. So that's why it's important to say, yes, but what is the effect size? What significance does it have in other ways rather than statistical significance? And the effect size is used in those meta-analyses. So that's what people do in those, when they're looking at studies from different laboratories published in the literature. There might be somebody who's used a certain independent variable, looking at stress, for example, someone else who's used a different scale, and many different laboratories or methodologies have been carried out. But if the effect size, which is after all standardized, it's a standardized measure, if that has been presented, then you can actually begin to combine them and do your meta-analyses. So that's, again, why the APA is so keen for studies to report the effect size, in case subsequently somebody wants to do a big meta-analysis. So that was Cohen's D. So that D is for the t-test. So you take one, remember t-test compares two means. You take one mean away from the other and you divide by the standard deviation. That gives you your D. And that's point. Oh, I've got it in the notes. You divide one mean by, take one mean, say if you're doing a t-test and you wanted to know the effect size, for a between participants t-test, you would take one mean away from the other, you're looking at the differences between the two means, and you would divide by an estimate of the standard deviation. Within subject designs, slightly different, but still the same basic principle. 0.8, if you get an effect size of 0.8, that's considered large. And you could just use those as rough guidelines. With my PhD students who were going to do a program of research, obviously based on a few things in the literature, I got them to work out the effect size by going to look at previous studies to see what kind of effect size might they be expecting in their first study for their PhD. And they were able to use that to calculate sample size. I'll talk about that in a minute. Okay, so we reminded ourselves about D, which you probably touched on last year for effect size. You can get an effect size with ANOVA. When we move to these more complex designs that I've been teaching you this semester, you can also get a measure of effect size, and it's called eta squared. Well, I think actually partial eta squared. There. So it's not D anymore, because we've now maybe got 3 or 4 or 5 conditions, or possibly 2 factors. That's what we've been learning. And our measure is called partial eta squared, and it's actually a correlation ratio. It's a little bit biased, and it will give us a rough idea. The way you would work it out, although you just have to click a button in SPSS, so don't worry about it, but what it's doing is looking at the squared correlation between the independent variable and the dependent variable. It gives us a proportion of variation in the data accounted for by the independent variable. So we're going to look at a proportion. Just like R squared is, isn't it? R squared, when we're doing correlation or regression, we see R squared, and I said R squared will represent the proportion of variability in the dependent variable that's accounted for by the predictors. So we've got something similar going on in here. The proportion of variation in the dependent variable, the data, that you collected, which is going to be explained or accounted for by the IV. So similar concept. And the way you work it out for a one-factor ANOVA, do you remember sums of squares for ANOVA? Remember sums of squares? What you do is you take the sums of squares between groups and you divide it by the sums of squares between groups and within groups. Remember between and within? So that's all that's happening to get partial eta squared. Sums of squares, so between the groups, divided by the sums of squares between groups plus within groups. And I haven't got the printout there, but just take, when we did that naming data, actor, actor plus character, actor plus series, I looked in the table from the ANOVA, okay, so I didn't work any of these out by hand. I looked, remember the dependent variable is milliseconds. Between groups, sums of squares is this, within is that, and if you add those two together, you get that. So if you divide the between this by that, you get that. Right? So between plus within, so the bottom bit of the equation, is 46485. So if you divide the between by the between plus within, you get 0.207. And so that's telling you that about 20% of the variability in millisecond, in naming times, measured in milliseconds, that's the dependent variable, naming times. So 20% of the variability in the dependent variable is accounted for by the learning manipulation in that experiment. So how much unexplained? Yeah. No, approximately 80% of the variability in naming times remains unexplained. Individual differences, do you think? All sorts of other reasons why there's a lot of variability. So our learning manipulation, actor, actor plus character, actor plus series, explains 20%. So small effect size, don't you think? Quite small effect size. So, you can ask SPSS. You're not going to have to do it by hand throughout your career, research career. You can actually ask it SPSS during the ANOVA. You can ask it for the partial meter squared. You'll find it in options, I think. So I think I've given you an example in your additional notes. So again, you could do that for both labs if you wanted to. You could get a measure of effect size and make a brief comment. 20%, only 20%, or it was quite a small effect size, so there must be lots of other relevant, variables influencing the dependent variable. Yeah, and of course the effect size, your correlations are the effect size. If you're doing the mindfulness lab, you've already talked about this. Okay, so that's effect size. And then I'm just going to finish up talking a little bit about power. So did you do anything on power last year? No? Not sure about that. Well, you probably even heard me say, oh, there probably wouldn't be enough power with only 10 participants. Power is particularly relevant if the effect size is small. So when my PhD students came to do their first study, as I say, I sent them off the literature to try and see if there were related studies. Could they work out an expected effect size? So based on some other publications in the literature, they were able to say, well, we're expecting a small effect size, or I'm expecting a moderate effect size. But can you see that if your effect size is very small, if you're only expecting a very small difference between some conditions, it's going to be quite hard to pick that up. You need to have quite a sensitive experiment if you're only expecting a small effect. By contrast, if you know that an effect size, based on past literature, say, is going to be very large, then you probably, you're going to have quite a lot of power to pick that up, even if you've got quite a small sample size. So, power is a very relevant issue. It's the ability to detect an effect, if there is one. So that's how people can define it. Power, if you say that, oh, that study had a lot of power, then it had a high ability to pick up an effect, if there is one. In other words, to correctly reject a null hypothesis. So we're back on significance testing here. Okay? And usually power is measured from 0 to 1. SPSS does give it if you click the button, but it's not very useful what SPSS does. It's much better to calculate your power before you run your study. So SPSS will give it after you've analysed your data, but by then it's too late. What you really need to know, ideally, is whether or not you've got a sufficiently powerful study designed in the first place. So you kind of should do it beforehand. So there are power calculations. I'm not going to teach you, so I really just want you to be aware of this. A power of 0.3 actually means there's only a 30% chance of finding an effect. So assume that we have calculated some power and we have an effect size, and you bung it into some sort of equation, and it came out as 30%. That means you've only got a 30% chance of finding an effect in your study. That's very low, isn't it? So why run the study? So what you need to do is increase the power before you run it. So when you come to doing your third-year projects, you don't want to run a study with only 5 participants. You will not have any power. Power will be very low. So sample size is very relevant to power. And effect size as well. If you've got a nice strong effect size, your power will say if you're testing 20 participants will come out much higher than if you're testing a very small effect size. You might find you need 50 participants. So usually we like power to be about 80%. So we want to have an ability to pick up an effect, if there is one, around about 80%. So just for the moment, assume power can be worked out. I'm not going to show you how to do it, but you need things like effect size, sample size, alpha level 0.05, and so forth. So you can use effect sizes, just as I got my PhD students to do from past research. And so they were able to work out the number of participants they ought really to be testing for their first study. And lots of people don't do it, but it is advisable if you can to do that. And if there's some past research, then you can use the effect size those people have reported in their publication, and you can try and work out the effect size, the number of sub-participants. So you can increase your sample size, that will increase your power, or there are other ways to increase power. Don't test people in a noisy room with the drills going outside, for example. That's going to make them distracted, a lot of variability in the data. If you've got a lot of noise or variability in the data, then it's much less likely you'll pick up an effect, because it'll be swamped by variability. You could use a within participants design, because within participants design are just that bit more sensitive, aren't they? Compared to between participants design. So you could change your design, but that's not always possible. It depends on what you're looking at. So those are some examples of how you could increase power, and you do need to be aware of that when you think about your project next year. And just get an idea, even though we wouldn't expect you to work out power, it's good to be aware, that you test everybody in the same way, you don't alter the procedure, or have your friend test the person who arrived at 9 because you couldn't get there in time. All that's going to introduce a little bit of variability, isn't it? If you alter the methodology, where you test them, for example, will let a little bit more variability, or it has the potential to. So if you're running an experiment, for example, you would want to have sort of quite a tight controlled procedure, everything the same as far as possible, possibly adopt a within participants design if that's appropriate. So the issue, if you get a null result, you can see, suppose you got a null result and somebody said, well, you only had 30% power. How you can't really, what conclusion can you draw? You just didn't have sufficient power. So you can see how it's important, particularly when you get a set of null results. Because what can you argue from a set of null results? Very little. Particularly if you haven't got appropriate power in the study in the first place. If, on the other hand, you've got a set of null results, you haven't been able to reject the null hypothesis, but you could say, but I designed the experiment to have power at 0.8, 80%, then you're on much firmer ground to say the IV has not affected the DV, or has a negligible effect. You're on much stronger ground if you have high power, if you've got a set of null results. Oh, that's it. So that's the issue of power. All of those things will be, particularly power, will be useful for next year for you when you're thinking about your study, whether it's a questionnaire study, if you're doing empirical work, you need to have a rough idea of power, but you wouldn't be expected to calculate it. But just knowing that testing 5 or 10 participants is not going to give you very much. So I'll do a drop in next week at 9 for those of you who want to come ask any questions either on confidence intervals or on the regression. And if you can allow to go that extra maybe between 12 and 1 to allow James to do what he wants to do with it. Okay, and I will put the portfolio exercise in under assessment. I'll probably try and put it in week 8 as well. We're already on week 8. Yeah. So I'll put it in 2 places, that's nearly done, and then you